Week 6, we're here. This is the part of the class we're really going to kind of shift from this perspective of looking at how we use resources. In the we talked about population and where they come from, geology, and some kind of fundamentals of resources. But at this point, we're going to kind of shift gears and actually spend some time examining individual resources. The first largest group that we're going to talk about are what we consider energy resources, and a subgroup of that, the thing that we're going to talk about initially, are different types of fossil fuels, right? You hear that all the time. Fuels essentially derived from fossils, from organic life. We'll get into the details and talk about how that works in a second. So I wanted to rehash some of the things we've talked about just a little bit. So this notion of energy, right? Because that's what we're going to be talking about. Energy. We've talked about it before. Hopefully you remember kind of the fundamental definition of energy is that it's work done by a force, right? We've talked about joules. It's kind of fundamental unit of energy. So again, joules, fundamental unit of energy. Joules applied over time. That was the next fundamental bit of energy that we talked about, the next unit. Remember, that was a watt, right? A joule applies, like a joule second, I guess, if you were to think about it that way. So in the sense of energy, we talked about it in pretty vague terms. It turns out there's some specific types of energy. We'll highlight just a couple of here that are fairly easy to understand. So we can talk about gravitational energy, right? So the gravity pulling down on something imparts energy to it. You can see in this cartoon of a little cart here, if you had a weight suspended by the pulley in the diagram and gravity is going to be pulling down on that, the cart will propel forward, right, doing work. So that's a good example of gravitational energy. The next one that we'll talk about is electrical energy. And this generally has to do with the concentration of electrons in a wire. We're going to have to look at in more detail at that as we go forward. But the imbalance of the electron concentrations can create a flow, or that force is the imbalance, and the flow is those electrons trying to balance out that imbalance. Thermal energy, right? So you can see heat transfer. There's a couple of different ways that we can derive energy from heat transfer, particularly with geothermal, right? So we'll talk about that, in probably 3 weeks. Maybe 3 weeks, 4 weeks, sometime down the road. Another one to include in this list is energy from light. And you can see here's one particular apparatus. You can see in this little bulb there's a rotating piece, and as light hits the black portion of those little panels, you can see inside it will cause it to spin. It's called a light mill, kind of like a windmill, right? But it's using light energy. Also lasers, right? Lasers are light doing work, so concentrated photons. Those are just to name a few, right? There's lots of different types of energy out there. You can actually see here in this diagram, this is showing kinetic energy on the right-hand side, which is movement, right? So things that are moving. And then also you have potential energy. Of course, gravity falls in the potential energy. And maybe this is giving you flashbacks to your first semester of physics class, or the difference between potential and kinetic energy. Concerning those types of energies that we saw, hopefully you started to realize that energy can easily be transformed from one form to another, right? In the case of the little cart, we had gravitational energy, potential energy acting on that weight. Then as that weight responded, it was transferred to kinetic energy. And that happens in lots of different ways, right? There's lots of different ways that energy can be transferred or converted from one form to another. But when that happens, it's not always super clean. And by not clean, I mean there's almost always some percentage of that energy that's lost or converted to heat. You can see here that the best example actually is our old friend, the incandescent light bulb. We've all seen a regular old light bulb like this, not one of the fancy expensive ones. So what happens in this case is there's electricity run up one of the wires and pulled out kind of the other wire down the bottom. And as that energy is traveling through this wire, the wire gets excited and it starts to emit radiation. But one of the problems with these incandescent bulbs, and one of the reasons why we're trying to get away from them, is that they actually lose about 90% of their energy in the form of heat. So in the context of energy efficiency, these things are actually pretty terrible. And I mean, you've probably learned this yourself, right? One of these types of light bulbs gets burned out, and you get out your ladder and you climb up and you grab onto that light bulb to switch it, and it burns the heck out of your fingers. It's because all of that energy, well, 90% of that energy has actually been transferred to heat rather than light. So again, we're better at this now, right? So engineers have figured out other ways to do that. And actually, light bulbs are a really easy way to look at this use of energy efficiency. So this is a pretty cool diagram that shows different types of light bulbs. You know, in the upper portion, use great photos of them, and then in the lower portion, it's the infrared, so it's the amount of heat released from those light bulbs. And you can see on the far right-hand side, we've got a 200-watt incandescent bulb. Next to that is a 100-watt incandescent bulb, 60-watt. CF is compact fluorescent, little curlicue, pigtail sorts of ones. And then on the far left, you see LED, which is light-emitting diode. Now, those, when we start looking at CFL and LED, essentially what happens is they're emitting energy primarily in the the portion of the electromagnetic spectrum that's visible light, and less of it is emitted in the infrared spectrum, where when you look at the typical incandescent light bulbs, the infrared is all over the place, right? It's a huge amount of heat lost. So we'll actually take a look. Here's a second diagram. No fun infrared lighting here, but you can see it's got 4 different types of light bulbs and their efficiencies. So there's a little pink bar above each of these images, and they're actually showing the percentage of the energy that light bulb consumes that's released as heat. And then the little yellow bar next to that is showing the percentage of energy that light bulb is using and converting to visible light. So actually, even in the LED, you know, if we look on the far right of this diagram, even the LED emits infrared radiation as heat. But notice that it's, first of all, the overall usage is pretty small, and it's about 50-50, right? So we kind of generally think about LED bulbs as being about 50% efficient, meaning about 50% of the energy they consume is lost as heat. But what's important to kind of couple with that is the fact that they use less energy overall, right? So they're converting less to heat, and then overall they're also using far less energy. So in the current world market, when you go to Home Depot and look at the light bulb aisle, LEDs are the best way to go, but there's a downside, right? Anyone who's tried to buy an LED light bulb realizes that they can actually be pretty spendy. But actually, I wanted to highlight something here that's an offer from our local power company. So at the risk of sounding like I'm advertising, I don't want this to come across that way. But we're talking about energy efficiency and energy use. So our local utility, Idaho Power, has actually decided that it's better for them if we as consumers are using less energy overall. And actually, they have an energy savings kit. So hopefully I'll get this figured out. I'll put the URL at the bottom here, or you can just Google it. That's probably far easier. But if you go to the Idaho Power website, and you can only do this once per household, but you can sign up and they'll actually mail you a box of LED light bulbs, which are in the range of $10 or $15 a piece. So it's actually a significant savings. A couple of years ago I did it in my house, right? We're converted to LEDs. So you can get your hands on some LED super high efficiency light bulbs for no cost, right? Just for being an Idaho Power customer. So I'm not a company shill, don't get me wrong. Thinking about what we've talked about so far, you might be a little bit confused, right? We've been talking about energy and all these different types of energy, but I haven't really talked about electricity. So how the heck do you create electricity, and what the heck is electricity in the first place? Well, it's going to require a little bit of chemistry, but fairly theoretical, nothing too crazy. And actually, I've got a diagram here you can see. It's larger than the one that I've drawn. But it turns out there's very specific chemical bonds, and shown here, this is an example of a metallic bond. So this is the type of bond that we see in metals, which occur geologically. And there's a fixed network of nuclei, right? The nucleus, or basically the mass of the atom. And the electrons are kind of free to do what they will. So you can see this is my tiny little drawing of metallic bonding. Then I'll go ahead and add some arrows that show how those electrons are kind of moving around within that metal. Chaos, right? So in the absence of a force, which we're going to get to in a second, the electrons in this situation are all kind of moving around the place. So they're excited, they're moving around, they're having a party. But none of them are going anywhere in particular. If you see, they're all kind of all over the place. And that's really kind of the resting state of the electrons in a metallic bond. They're kind of just swirling around all over the place. And so I'm going to draw another diagram, which is going to be a really, really, really close-up view of a piece of wire. And then I'm going to add some electrons to that. I'm not going to draw the nuclei like I had here. So, beautiful piece of wire. As I said, we're going to zoom way in. And really, I just drew a couple of dots in here to indicate electrons. Obviously, I didn't want to spend too much time. Lots and lots and lots of dots. And also, I didn't want to mess up my drawing with all of these different arrows like I had in the last one. But you can picture in your mind all these electrons wiggling around, but collectively doing nothing, right? You know, the directions kind of cancel one another out. They're all scurrying, but no one's really leading the charge. They're not all doing kind of the same thing. And so that's where we start to get into the notion of, well, how can we make all those electrons do the same thing? And it turns out the answer is in a magnet. So we have our big, powerful bar magnet here, our piece of wire with some electrons in it here. And if both of those are, well, first of all, I guess to back up, first of all, notice I've drawn the magnetic field of our magnet here. And we also know that electromagnetism creates not only a magnetic field, but an electrical field. I don't want to get too far into the physics of that, so you can save that for a different class at a different time. But here, if our bar magnet is stable, these electrons just exist within its magnetic field, and again, they just kind of do nothing, right? But one of the things that's really interesting, and of course we discovered this in the 1700s, Faraday among others, right? Some of those really famous, influential physicists, he figured out that if you move this magnet, so if the magnetic field is actually in flow or moving, something really interesting happens. At that point, all of the electrons react and either move away or toward, depending on if it's what end of the magnet we have. So let's say our magnet moves closer to our wire. Well, all of these electrons are going to respond in the same way. The result? Flowing electrons. We actually call this inducing or creating a current. So this is induction of a current, right? So now, again, the current, the flow of electrons allows us to do electrical work. You hear that term current often, right? An electrical current, which is a flow in a similar way that a river has a current, right? It's just a flow of electrons. And this is the basis of our modern electrical society, right? This is the fundamentals of electricity. You're going to watch a little video, a recently unclassified video by the Navy, which is pretty fun. Hopefully you'll like it. Kind of about how this works. But again, what we're going to spend the rest of the semester doing is basically looking at this. So what you're going to hopefully find out, and I'm going to use this catchphrase for the rest of the semester, spin the magnet, right? So remember that if our magnet moves towards our wire, all of these electrons will move. But if you move that magnet and stop it, then the electrons won't move anymore. They're only active when the magnetic field is in flux or is moving. So Moving a magnet once will push your electrons, but then it's over, right? So what we really would like to do is to have a magnet be constantly moving. And we do that, right? That's exactly how we generate electricity. We spin the magnet. And usually there's coils of wire involved. And again, that's maybe the realm for an engineering or a physics class. But the more wire you have, the more portions of that wire that the magnetic field is crossing through, the more electrons it's going to push and the stronger the current will be. There's even some other things. The stronger the magnetic field, right? So if the magnet's bigger, it will create a stronger current. Again, when we think of, let's think of coal, for example, right? So we're not quite at coal yet, but it's a rock that burns. So the way that we use coal is we take that coal, we burn it, and we boil water with it. Again, I'm leaving out some of the ugly details, but we boil water, and then that water creates steam. We use that steam to spin a magnet. That's the whole thing. In the case of generating wind power, we use the wind to spin the magnet. In the case of nuclear power, we take radioactive uranium, it's really hot, and we use that to heat water up to the point where it turns into steam and we spin the magnet. In geothermal electrical generation, we take hot water out of the ground, keep it pressurized, flash it to steam, and use the steam to spin the magnet. So it's all basically the same, with the exception of photovoltaic, which we're going to get to, like I said, 4 weeks down the way. But all of the different types of energy production, in a conventional sense, spin the magnet and create a current and make electricity for us to play with our iPhones, right? No, to have lights on and to cook our dinner and do all kinds of other things. So for the last part of this video, I wanted to talk about types of energy in a different way than we did at the beginning of this video. So I showed you this, a diagram that had potential energy and kinetic energy and all of these things, again, really from your first semester of physics. But actually, if you take a look at this next diagram here, these are the types of energy that we use for heat and electricity generation. And notice that they're actually broken down into two very broad categories, which we can thank for our energy use. So you can see on the top right, we've got gravitational energy, ocean tides, geothermal, hydroelectric, right? Those are all forms of gravitational energy. So again, hydroelectric is energy that we pull out of water that's flowing down its channel. Well, it's flowing down its channel as a response to gravity, right? So ultimately, that's gravitational energy. So nuclear energy, we really talk about it in two different ways, right? So the decay of uranium specifically, but also thorium and a couple of other things, that decay reaction produces heat. We use that heat directly to, turn water into steam and spin the magnet, as we were just talking about. You can see that's this kind of isolated path of nuclear that we have, from nuclear straight to nuclear to electricity. There's also nuclear or radioactive decay occurring inside of the Earth. When we talk about geothermal energy, the energy in that water was initially created by radioactive decay, ultimately in the outer core. The inner core too, but primarily in the outer core. Then you can see the nuclear kind of cascades down from there. So the type of energy released by the sun is nuclear energy. It's fusion, right? There's a fusion reaction. Two atoms getting stuck together so hard that they fuse and become a new atom. A little bit of energy gets spit off. That's what sunlight is, right? It's lost energy from hydrogen fusion reactions. We've not been able to create fusion yet and use it for humanity's purpose, but you can see here some portions of the Earth get heated up more than others. The difference causes wind. We've got photosynthesis, which is plants. So we've got coal, which is derived from plants. We've got animals that eat those plants, so oil is derived from animals. Solar radiation. anyways, lots of different types of energy here. And again, we're going to spend some time over the course of the semester going through that. The last thing I wanted to talk about are these two diagrams. We'll look at this one first. This is world energy consumption. So we talked about world populations and things along that line. In the case of world energy consumption, this isn't a raw population game. This is an example of per capita use, right? So as we actually have people developing, in these what we call emerging countries or industrializing countries, people are actually consuming far more electricity per capita, right? So this isn't quite the same game as the population growth where we see it level off. This is this kind of always increasing consumption of energy. But then the last diagram we're going to look at is a diagram that shows world energy consumption in a couple of different types of power, right? So we've got coal, oil, right? We use oil for lots of electricity. Coal is falling out of favor, right? So when we look at coal, last year, the 6th largest coal company in the United States went bankrupt, right? They declared bankruptcy in October of 2018. So coal is a problem, right? It's heavy. We can't put it in pipelines. We got to put it on trains. It's really dirty. We'll get into some of those examples. So coal is really kind of had its day. Renewables, you can see increasing here. We can even look at some other diagrams where it increases a little bit more. And then nuclear is really viable, but it has an incredible PR issue. So again, we'll examine all of those going forward. All right, and I'll see you in the next video. Bye.